Hey guys,
Hey, Professor.
how's it going?
Busy.
Yeah, it's things ramp up pretty quickly, especially in spring semester, huh?
Yeah.
Good. Yeah, just chugging along. How are you? Yeah, sounds good. How's your daughter doing?
She's good. She's getting bigger. She's gonna be 8 months in a couple weeks.
Wow, nice.
So yeah, she's growing up fast.
That's must be tough to have a newborn during this time. My
Oh,
fiance's brother has a newborn also. Like I think he's about almost same age as your daughter actually. I think he's about 7 months now.
uh,
Yeah, it's they worry about it, all the time.
yeah, it's tough. Definitely is a struggle, but what can you do?
Okay, it's 2:30, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today?
Good. How are you?
Good, good.
Yo, Fessy.
Yep, it's our fourth lecture here for heat transfer. So, it feels like we just started yesterday, but we're already kind of in full swing. Okay, so today the plan is I had one more example I wanted to show you with thermal circuits in planar cases. So we're going to do that. And then after that's done, we're going to start our next set of lecture notes, which is lecture notes 02 on radial heat transfer. So basically, the idea with radial heat transfer is taking the same ideas, heat equation, thermal circuits, everything that we just went over for the last two lectures, but then apply them to radial systems. So we're talking like cylinders and spheres. And so the ideas are all going to be the same. It's just the coordinate system is going to be different because we're going to be in cylindrical and spherical coordinates, which I know is always really scary. Even I still get a little bit worried whenever I have to do problems in cylindrical and spherical coordinates. But what you'll see hopefully is that after we do some examples that you'll have some confidence in doing this. Okay. Okay. And so the first homework is out there right now too. So that was assigned on Monday. And so that's going to be due this following Monday at 11:59. Okay. All right. So before I get started with the lecture today, are there any questions I can answer either from last time or on the homework? Okay. But as always, if there's any questions throughout today, just, feel free to ask anytime. Okay. And so when we left off on Monday, we were discussing, how we can use thermal circuits, right? And so the idea of a thermal circuit is to kind of simplify our heat transfer analysis, right? Because so far, what we've mostly been using is the full heat equation. So that's, a differential equation where we have to solve by integrating and applying boundary conditions. But a lot of times, we want to perform heat transfer analysis without having to dip into differential equations. So thermal circuits provides a way to, perform, get the exact same numbers, but with only performing algebraic calculations instead of differential equations. Okay? I won't say that it's necessarily shorter a lot of times than doing the heat equation, because sometimes, the arithmetic and the algebra can get kind of intense, but it's just intuitively, I think it kind of makes a little bit more sense. Okay. And so let's do an example, which is, I think, a little bit of a step up in complexity compared to what we did on Monday. Okay. Okay. And so in this example, where the setting is going to be, we're inside, say, like a material or chemical treating plant, or maybe like a chemistry lab. Okay. And so the situation kind of looks like this. And so we have a planar system. Okay. And it has two different layers. Okay. And so this bottom layer here will be called the substrate layer. Okay. And so that's kind of, maybe some chemical substrate that you're working with as an engineer, like as a chemical engineer or, processing engineer. Okay. And then on top of the substrate, we have a thin film. Okay. Right. And so a film can either refer to maybe a thin layer of fluid that's on top of the substrate, or maybe a thin layer of like glass or plastic. Okay. And then each of these have their own lengths. Okay. And so we'll say that the length of the substrate is given by LS, and then the length of the film is given by LF. Okay. And they have numbers here. So let's see, LF is going to be 0.25 millimeters. Okay. So it's a quarter of a millimeter thick. So it's very thin. And then the substrate here is going to be 1 millimeter thick. Okay.
Sorry, what was a substrate?
So the substrate is just you can just think of it as a just another solid where heat transfer is going to occur. But in some applications for this might be like I'm drawing a blank right now. But it's it's basically a chemical that we want to work with. And we want to the idea with this example is we want to bond this film to this substrate. Okay, so we want to kind of form them together. So maybe like we're in a plant where we're manufacturing contact lenses or something like that. Okay.
Okay, thank you.
Mm-hmm. Okay, and then on top of this of these two, we have air that's flowing over the top, and so this air, let's say air, has its own temperature. So the temperature will be T infinity, and it has its convection transfer coefficient H, okay? And then the film and the substrate also have their own thermal conductivities, okay? And so the film has its thermal conductivity Kf, and then the substrate has its thermal conductivity Ks, okay? And so the values for these are given by the following. So Kf is going to be 0.025 watts per meter K. And then Ks is going to be 0.05 watts per meter K. Okay. And then for the air, we have an ambient temperature of 20 degrees Celsius. Okay. And so that's going to be our T infinity. And then our H here is going to be 50 watts per meter squared K. Okay. Okay. And so the situation here is we want to bond these two together. So we want these guys to basically chemically bond. Okay. Okay. And then through, some chemical analysis, maybe you're working with a chemist, he says in order for them to bond, the interface between the substrate and the film has to be maintained at a temperature of 60 degrees Celsius. Okay. And so basically what that says is that, this interface right here, or the temperature of this part, which I've circled in red, this has to be 60 degrees Celsius, okay? Oh, one thing I forgot to mention is we know the temperature at the back of the substrate, okay? And so at this surface right here, we know that the temperature here, which I'll call T1, okay? T1 is, 30 degrees Celsius, okay? And then this T, we'll call this TS. TS has to be 60 degrees Celsius. Okay. Okay. And so the way that you're going to, apply or make this interface 60 degrees is you're going to apply some heating to it. Okay. Okay. And so the heating is actually going to be applied through a laser, okay? And so the laser is basically going to be shining down onto this interface. And so it's going to pass, you design the laser such that it passes through the film and it applies the heating straight at this interface, okay? Okay. And the heat flux for this interface will be basically what we're going to be solving for. Okay. Right. And so given the situation, what we want to do in this example is solve for that heat flux such that we can maintain an interface temperature of 60 degrees. Okay. Okay. And so this example here, there's kind of a lot going on. So we have basically three different mediums, right? So we have the air on top, we have the film, and we have the substrate. Okay. And so this would be a problem that'd be, really difficult to solve with the heat equation, just because there's, several different materials. But, this is a lot simpler to do with a thermal circuit. Okay. Okay. And so our first step in this problem is going to be to actually draw out that thermal circuit. Okay. Okay. So let's go ahead and draw this. So we have two solids here. So we have the substrate and the film, and then we have the air that's on top. And so that's going to give us 3 resistors. Okay. Right. So let's go ahead and do that. When you're doing these thermal resistance problems, whenever you have a, a solid surface or solid material, okay, you can use one resistor to basically model that, okay? And remember that whenever you have convection cooling, you need to have a resistor to model that as well, okay? Okay, and so the next thing we need to do on this circuit is to label the temperatures at the endpoints, okay? And so we'll call the left side of the circuit, we'll call that T infinity. And so that's the temperature of the air. And on the right side, we'll call this T1, which is the temperature on the bottom of the substrate. Okay. Notice how I chose basically the two end temperatures here. Okay. So on the very top here, we have T infinity. And so that's why I chose T infinity to be on one side. And on the other side, I have T1, which is the very bottom of our geometry here. Okay. And so those are always going to be your 2 end nodes. Okay? And then from here, what we need to do is we need to list out the resistances of everything that's in between these guys. Okay. All right. So the first resistance that we have is the convection resistance of the air. Okay. Then after we pass through the air, we pass through the film. Okay. And so we're going to have our film. And then after we pass through the film, we're going to have our substrate. Okay. And then we'll write, expressions for these on the next page. Okay. And then for this problem, we know that we also know one other temperature, which is the temperature right in between the film and the substrate. Okay. And so that's going to be represented by this node right here. Okay. And so this is TS, which is 60 degrees. Okay. And then to this CS, since the heating is being applied to this layer right here, we know that Q naught double prime is going to be applied right here. Okay. Okay. And so now that we have this circuit right here, we can start to use this to solve the problem. Okay. All right. Any questions on this?
Just a quick question. Is anything supposed to be in between our air and our film?
Yeah. So there's a temperature there too, and so we can call this our T top, I guess.
Okay.
And so there's a temperature there. It's just that in this case, we're not really interested in solving for it. But
okay.
Yeah, anytime you have a node in between resistors, there's always a temperature there. It's just a lot of times it's you don't always are interested in that temperature there.
Gotcha. Okay, thank you.
Mm-hmm. Okay, so let's go ahead and start solving this. Okay. Okay, and so at this point we need to start using our circuit to compute the heat transfer, right? And so if we kind of go back here and look at our circuit, right, we know that TS right here, TS is the highest temperature in our system, right? So that's at 60 degrees. And so we know that, because it's the highest temperature, heat is going to go and flow from this node out in both ways, right? Because remember, heat always goes from high temperatures to low temperatures. And so, when we apply our heating to this intersection, you're going to have one path of heat go up towards the air, and you have one path of heat going back towards the bottom of the substrate. Okay. And by conservation of energy, we know that the applied heat okay, this is the heat that we're going to apply. It's going to be equal to those two heat paths that I just mentioned there. Okay. And so we're going to have Q towards the substrate. Okay. And we're going to also have Q towards the air. Okay. Okay. And so in order to basically solve for the heat that we want to apply, we need to solve for both Q substrate and Q air. Okay. Okay, so let's start with Q substrate because that one's a little bit more straightforward. Okay. Okay. All right, and so at this point we can start using the expressions in our circuit. Right? So if we go back here, we can see that Q that goes to the substrate is going to be this path here on the right. Okay. And so the way that we compute heat transfer from a thermal circuit is we take the difference in between the temperatures. Okay. And so in this case, the nodal temperature is going to be Ts and T1. Okay. And so Q substrate is going to be Ts minus T1. Okay. All divided by the resistances in between them. Okay. In this case, we only have one resistance, which is just the resistance of the substrate. Okay. Okay. Which, if we plug in for this, we know that our formula for resistance is going to be L over Ka. Okay. Where L, remember, is the length of the material, K is its thermal conductivity, and A is its cross-sectional area. Okay. Okay. And so if you notice from the problem, I didn't give you any areas, right? So there's no cross-sectional area here. But we actually don't need it because everything that we're computing here, notice I gave double primes to everything. Double prime means heat flux, right? And so actually, this formula is technically like this, where, this resistance heat transfer formula is actually the heat transfer rate. So it's actually not the heat flux. And so remember, the way that we get heat flux is we take heat transfer rate and we divide it by area, okay? And so let's go ahead and do that. And so we can say that Q substrate double prime is equal to Q substrate divided by A, right? And so if we plug that into our expression here, we have Ts over T1 all over A times L over Ka, right? We see that the areas cancel out, and then we don't need to worry about the area, okay? Okay. And so we plug everything in because we know Ts is 60 degrees. We know T1 on the back of the substrate is 30. Okay, so this will be 60 minus 30. Okay. And then on the denominator, we need to know the ratio of the length of the substrate over the thermal conductivity, which we can get from the parameters of the problem. Okay, so we just take the division of 1 millimeter divided by 0.05. Okay, and so it's going to be 0.001 meters divided by 0.05 watts per meters K. Okay, and we plug all that into our calculator, and what we get is 15 watts per meter squared. Okay, and so this is the heat flux that's going through the substrate. Okay, and so now we've computed the first part of this equation here, and so now we just need to compute the heat flux that goes towards the air. Okay. Any questions on this part here? Okay. All right, so now let's compute Q air. Okay. Let's compute the heat transfer rate to the air first, just because we're going to use our thermal circuit for that. Okay. And so we're going to do the same thing. And so Q of the air is going to be the difference in the temperatures in between those two nodes. And so we have Ts minus T infinity. Okay. And then on the bottom, we write out the sum of all the resistances that lead there. Okay. And so in the case of the air, we actually pass through two resistors, right? So we pass through the resistor of the film, and we pass through the resistor of the air. And so we need to sum up those two guys. Okay. And so Q. Oh, go ahead.
Sorry about that. So we just ignore T top because, like you said, we're not interested in that.
Exactly. Right. Yeah. Yeah. So you can compute T top, and so that's something you can compute here. But for this problem, we're just not that interested in it. Okay. And then we can plug in the expressions for these guys. So our film which again is a solid. And so we're going to use the resistance for a conductive solid. And so this can be LF all over KF times A. Okay. And then for the air, we have a convection resistance, where convection resistance is going to be 1 over H times A. Okay. Okay. And then just like we did for the substrate, we're going to compute the heat flux. And so we said that Q air double prime is equal to Q air divided by A. Okay. And so this area here is going to cancel out with these guys. Okay. And so we get that Q air double prime is equal to TS minus T infinity all over LF over KF plus 1 over H. Okay. And then, you know, we have all these things in the problem, so we plug everything in and we get 1,333.33, repeating, of course, watts per meter squared. Okay. Right. And so now that we have Q substrate and Q air, all we have to do is sum those up in order to solve for Q naught. Okay. So we have Q naught is equal to Q substrate plus Q air. And then what we get is 2833.33 watts per meter squared. Okay. All right, and so that's a good example there on how you can use a thermal circuit to kind of simplify a problem with lots of different layers like this. Okay. Any questions on this before we move on to cylindrical heat transfer?
So we could apply that for like on an engine or when we look at engines and whatnot.
Yeah. So anything that has multiple layers where you have heat that's passing through, thermal circuits work great for these because they handle those things really easily. Because anytime you have a separate layer, you just use a resistance for that to represent that. Mm-hmm.
Okay, thank you.
Mm-hmm. Okay. So that's everything with planar conduction. So with that, you know, that's everything that's going to be on the first homework. And so from here on out, you know, the radial systems is going to be on the next homework, which I'm working on right now. Okay. Okay. So let's start doing this. So this is going to be steady state conduction. And so today we'll do cylinders, and then next Monday we'll do spheres. Okay. Okay. All right. And so, you know, we can draw, let's start by drawing a cylinder. Okay. And so we're basically be looking at the cylinder kind of head on like this, right? And let's, just for you know, generality, let's assume that we have a hollow cylinder, okay? And so the inner radius of the cylinder is going to be Ri, and then we'll say that the outer radius is going to be Ro, okay? And so we have kind of like a donut that kind of extends out, okay? All right, and so the big assumption that we're going to be making in these radial systems is that we're going to assume that the heat only travels radially outward, okay? Or inward too, I guess. And so visually, it kind of looks like this. And so let's say that we have, you know, heat that comes out like this, okay? Okay. And so the heat is basically, we're going to assume that it only goes in the R direction, okay? And so if you kind of remember your cylindrical coordinates, in cylindrical coordinates, we have 3 different coordinates, right? So we have R, we have theta, and we have Z, right? Where theta is kind of this direction that goes around the cylinder, you know, kind of like this. Okay? So that's your polar coordinate. and then Z is the direction kind of down the barrel of the cylinder. Okay, and so for everything that we're going to be doing for this week and next Monday, we're going to ignore theta, and we're going to ignore Z. Okay, so everything is just going to be strictly in the R direction. Okay? And what this does for us is that even though, you know, cylinders, you have heat going in every different Cartesian direction, when you put it in terms of cylindrical coordinates, this effectively makes our problems 1D. Okay. And we like 1D because 1D is simple. Okay. Okay, so let's start with kind of the same starting point that we use for Cartesian systems. And let's write out the full heat equation in cylindrical coordinates. Okay. Okay, so once again, you know, I'm not going to derive this guy just because it's, you know, I think there's better uses for our time. But if you are interested in looking this up, the book has a great explanation for the derivation. But basically, you know, you would basically just apply conservation of energy on just a small cylindrical element, and then kind of, you know, go from there. Okay. Okay, so the heat equation looks like this. We start with 1 over R, partial derivative with respect to R of KR, partial T, partial R. And so that's our derivative with respect to R. Okay. Then we have a theta derivative term. Okay. So that's 1 over R squared, partial theta, K, partial T, partial theta. Okay. Then we have a Z term. So that's partial Z of K, partial T, partial Z. Okay. We also have our thermal generation term, or thermal production. Okay. And so that has the same symbol as we did before. So that's going to be our Q dot. And then on the right-hand side of this equation, we have our unsteady term. Okay. So this actually looks like the same as the 1D case. We have rho, which is the density, Cp, which is our you know, specific heat, multiplied by partial big T, partial T. Okay. And so here's the full heat equation here in cylindrical coordinates.
Oh,
so,
wait, just double checking that P is a rho next to the C, right?
Yes, yeah, that's
Okay.
a rho, that's density.
Another question for the whole second term, is that delta or is that theta? I forgot my Greek letters.
It's theta, yeah.
Theta, okay. Thank you.
Yeah, so this is an intimidating equation, right? So there's kind of lots of stuff going on, but you know, luckily for us, we're going to simplify this significantly with our assumptions. Okay. All right. So first assumption that we make, which is kind of our first step, is we always assume steady state. Right? And with the steady state assumption, we can cancel out any derivatives with respect to time. And so that guy goes away, okay? Okay. And so the next assumptions that we're gonna make have to do with kind of what I've circled and crossed out right here, okay? And so since in these problems, we're only gonna consider just the radial direction, any derivatives with respect to theta and any derivatives with respect to Z, we can go ahead and cancel those out, okay? And so let's look at our equation here and find any derivatives with respect to theta and Z, okay? All right, so first let's look at our first term. And so our first term is 1 over R, partial R, K times R, partial T, partial R. And so all of these guys are R derivatives. So this guy is good. So this guy can pass, okay? And then we look at our next term, which is 1 over R squared, partial theta, K, partial T, partial theta. And so since we have a derivative with respect to theta here, we go ahead and cancel this guy out, okay? And the reason we're canceling this out is we're assuming that the heat flow is 1D and radial, okay? Okay. And then we look at our next term right here, and we see that there's derivatives with respect to z. And so we can again cancel this guy out. Okay. And again, the reason is 1d, and our 1d direction is radial. And so we're going to ignore z. Okay. And so all that we're left with here is the term with the r derivatives and the term with the thermal production. Okay. And then I'll write that out on the next page. Okay. Are there any questions on this?
Yeah, just so that's a plus at the end. Are you adding the q dot or?
Yes.
Okay.
Yes. Yeah. So the
Just
q
wanna
dot
make
is on the same side of the equation as the r derivative. Yeah. Mhm.
All right, thank you.
Yep. Okay. And so if we cancel out all those terms, our simplified heat equation looks like this. We start with 1 over r. And we have d dr of k times r dt dr, okay, plus q dot is equal to 0. Okay. All right, and so when you're solving heat equation problems in cylindrical coordinates, this is basically going to be your starting point here, because for all the problems that we're going to consider, we're going to assume a steady state, and we're going to assume that theta and z terms are 0. And so this is usually a good starting point right here. Okay. And so one other assumption that we often make for a lot of problems is we assume that there's no generation. Okay.
So, Professor, just clarifying. So when we're dealing with cylindrical, this is the formula we'll end up using, unless stated otherwise.
Yeah, exactly. So this is so when you're doing your problems, if you want to start from this formula right here, I think this is a fine starting point. But make sure that you mention in your answers that we've assumed that it's 1D in radial and we've assumed steady state. That way I know that you're starting here for a good reason. Yeah.
Gotcha. Okay, thank you.
Mm-hmm. Okay.
Also, the partials go away and then they just go to derivatives.
Yeah, great observation. So one other thing we did was we changed the partial derivatives to a regular derivative, because at this point, there's going to be no dependence on theta and no dependence on z, and so our temperature is just going to be a function of just one variable, which is r. And so since we only have one function variable like that, then we can change the derivatives to regular derivatives. Yeah.
Got it.
Professor?
Yep. Mm-hmm.
So the assumptions that we used in that is assume steady state, so that our partial derivative of time goes to 0. 1D, so we can get rid of our z. Radial to get rid of our thetas, and then no generation to get rid of the q dot.
Exactly. Yep. Mm-hmm.
Okay.
Okay. So that's the heat equation that we can start with, and so let's also compute the heat transfer rate. Okay. Okay. And remember the formula that we use for heat transfer rate is Fourier's law. Okay. So remember, Fourier's law looks like this. So Fourier's law says that Q is equal to minus K A dt. In this case, it's going to be a derivative of t with respect to r, because that's our distance coordinate. Okay. Okay. And in cylindrical coordinates, this can be simplified a little bit, or we can plug in for this, because this a right here. Remember, this a right here is the surface area through which we're transferring heat. Okay. Okay. And so since we're on a cylinder, the surface area that we consider is just going to be the surface area of that cylinder. Okay. And so we can plug in for A. The surface area of the cylinder is going to be just the perimeter of the cylinder. And so that's going to be 2 pi r multiplied by the length. Okay. And so that basically gives us the surface area on the outside of the cylinder. Okay. Okay. And then again, dt dr. And so if a problem asks you to solve for the heat transfer rate in a cylinder, this is the formula that you would use. You know, once again, noting that for area, you're going to plug in the surface area of the cylinder. Okay. Okay. And so that's the introduction to the heat equation. So let's actually put it in use here for an example. Okay. And so let's actually compute the temperature field for this exact situation, which I have on the front right here. Okay. And so let me redraw the figure here. And so in this situation, we have a hollow cylinder. And so our cylinder will have an inner radius and an outer radius. Okay. Okay. Right, so it's going to look like that. And then we're also going to say that the inner radius is held at a temperature Ti. And then the outer cylinder is held at a temperature TO. Okay. And so what we have is basically specified temperatures at both the inner and outer radius. Okay. Okay. And so mathematically, we can express these as boundary conditions. Okay. Right. And so we can say that T, when you evaluate it at Ri, is going to be Ti. And then the T, when you evaluate it at Ro, is going to be TO. Okay. Right. And so if we also assume that there's no generation, okay, let's use the equation that I have at the top right here to solve for the temperature field or the temperature distribution. Okay. And so what we want from this is basically a T as a function of R. Right. So we're going to integrate this expression up here, get our two arbitrary constants, and then use the boundary conditions to solve for those constants. Okay. Any questions on this example or this page before we get started? Okay.
I had a quick question on the heat transfer rate.
Sure. Mm-hmm.
L is in reference to length.
Yes. Yeah. So that's the length of the cylinder. So you can imagine, this cylinder goes into the page like this. This length is kind of this length right here. Yeah.
Okay. So even when we're doing it in the R direction, we would consider the length.
Right. Yeah. Because in order to compute the area, you need the length of that cylinder. So the heat transfer is only going to be in the radial direction, but your cylinder would still have some depth. And so that depth you would need to compute the heat transfer rate.
Okay, got it.
Mm-hmm. Okay. And so let's go ahead and get rolling. So if we assume that there's no generation, then we have our starting point is the heat equation that looks like this. So we have 1 over R ddr of K times R dt dr is equal to 0. Okay. Okay. And so this is a little bit more complicated than our Cartesian case because we have some extra r's floating around. Okay. So the first thing that we're going to do is we're going to factor out K from this derivative. Okay. Okay. And the reason we can do that is because K is just a constant. Okay. Right. And so since K is a constant, taking the derivative to it doesn't really do anything to it. So it's, we can just pull it out of the derivative just for simplicity. Okay. And so we're going to have K over R times d dr of R dt dr. Okay. All this is equal to 0. Okay. And then at this point, before we integrate, we can simplify this a little bit by multiplying both sides by R over K. Because we want to cancel out this term out in front right here.
Professor.
Mhm.
I guess we can't take out the t because that's changing.
Right, exactly. So yeah, so the T is what we're actually going to be solving for. So that's the temperature field. And so that is definitely going to be a function of R. So we can't pull that out of a derivative with R. And so the reason we can pull K out is because K doesn't change as a function of radius. And so taking the derivative of K, is not going to do anything. So we can just pull that guy out. Yeah.
Okay, thank you.
Mhm. Okay. And so on the left-hand side, we're going to cancel out the K over R. And on the right-hand side, we have 0 times R over K, which is just going to be 0. Okay, so we've effectively kind of gotten rid of that guy. And so what we're left with is d dr of R dt dr is equal to 0. Okay. And so this is nice right here because on the left-hand side, we have a derivative that's out in front, and there's nothing impeding that derivative. Okay. And on the right-hand side, we just have 0. And so from here, what we can do is we can just simply integrate. Okay. And so on the left-hand side, integrating DDR, just going to get rid of it. So the integral and the derivative kind of cancel each other out. And so on the left-hand side, we're left with R times dt dr. Okay. And on the right-hand side, we have integral of 0, which would normally just be 0. But since we are doing an indefinite integral, we have to put our arbitrary constant there. Okay. And so this is going to be equal to C1, which is our first constant. Okay. Okay. And so at this point, we have to divide by R just so we can simplify this side. Okay. Okay. And so doing that, we have dt dr is equal to C1 over R. And then from here, we can just integrate again. Okay. And then what we're left with is on the right-hand side, we have T of R, which is, what we wanted to solve for in the end, T as a function of R. And on the right-hand side, we have C1 times integral of 1 over R. And so integral of 1 over R is going to be the natural logarithm of R plus C2.
I have a question about this integral.
Sure. Mm-hmm.
So because we're using cylindrical coordinates, don't we have to introduce like a RDR from the Jacobian?
Yeah, no, that's a good question. So normally you would have to do that if you're kind of integrating, just kind of on the surface like that. But in this case, we're just integrating R as if it's kind of some dummy variable. And so we kind of already accounted for that RDR by starting with something that's already in cylindrical coordinates right here. And so any RDR system, or like I think sometimes it's 2 pi RDR, that's already kind of incorporated in the fact that we're starting with the heat equation in cylindrical form. And so if we actually derived this heat equation in cylindrical form, that's where it would come in. But since that's already been accounted for kind of in the derivation of the heat equation, then we don't have to do it again. Yeah. Okay. All right. Any other questions on this before we start to apply the boundary conditions? Okay. All right. And so now that we have our general solution here, we need to solve for C1 and C2 in order to get our full solution. Okay. Okay. And so our two boundary conditions here are specified temperatures. Okay. And so our first boundary condition stated that T at Ri is equal to Ti. Okay. And so if we plug that in, we get that C1 times natural logarithm of Ri plus C2. Okay. And then our other boundary condition, which is that the temperature at RO is just going to be TO. And so we plug RO into our equation. What we get is C1 times ln of RO plus C2. Okay. And so now we have a system of two equations that we need to solve for our two unknowns. Okay. All right. And so the easiest way I think to solve for C1 in this case is to subtract these two equations. Because if we notice, both equations just have C2 just kind of hanging out on its own. And so if we subtract these two equations, we can just cancel out C2 right away. Okay? And so if we subtract these two equations, you can see that the C2 on both sides is going to cancel out. And so on the left-hand side, we're left with Ti minus To. And then on the right-hand side, we have C1 times natural logarithm of Ri minus natural logarithm of Ro. Okay. And then from here, we can just divide both sides by ln of Ri minus Ro. Okay. And so we get C1 is equal to Ti minus To divided by ln of Ri minus ln of Ro. Okay. We can actually simplify this a little bit more by leveraging the rules of natural logarithms, okay? Because we know that if we have two natural logarithms and we're subtracting them, we can combine them together into one natural log and just divide the two, okay? And so kind of the simpler form for this is going to be Ti minus To, all divided by natural logarithm of Ri divided by Ro. Okay. And that is our simplest form for C1. Okay. Any questions on this? Okay. And so now that we have C1, we can go ahead and plug this back in and solve for C2. Okay. So we can do this to any of the equations up above. And so you'll end up with the same thing. Okay. And so let's actually plug it into the formula for TO right here. Okay. And so we have TO is equal to C1 times ln of RO, but we just solved for C1 right here. And so this is going to be Ti minus To divided by ln of Ri divided by Ro, okay, times ln of Ro plus C2, okay. And then now we can just, subtract both sides by this quantity that I have squared here in order to solve for C2. So let's go ahead and do that on the next page. But I'll give just a couple seconds if you guys are still writing it down. Okay. All right. And so if we move that over, we have C2 is equal to TO minus Ti minus To, all divided by ln of Ri divided by Ro. Okay. And this all multiplied by ln of Ro. Okay. And so we plug all this in. So we plug in for both C1 and C2. Then we have our final temperature distribution. Okay. And so our final temperature distribution is, we just plug in for C1 and C2, and we get T of R is equal to Ti minus To, all divided by ln of Ri divided by Ro. Okay. And this is multiplied by ln of R. And so that's our C1 term plus TO times Ti minus TO divided by ln of Ri divided by Ro times ln of Ro. Okay. And so that's the full solution right here. But obviously, you know, it's kind of a mess. And so what we can do here is we can simplify the logarithms. Okay. Oh, sorry, there's the minus sign right here. This should be plus TO minus this guy. Okay. Okay. Because what we notice is that these two terms right here have the same coefficient out in front. And so the only thing that's different here is the logarithms. And so we can kind of combine those two together in order to get kind of a little bit of a more simple solution. Okay? And so if we simplify those logarithms, what we get is T of R is equal to Ti minus TO divided by natural logarithm of Ri divided by Ro times natural logarithm of R divided by Ro plus TO. Okay. And so this is kind of the simplest form of the solution right here. Okay.
So I think if we use the other equation to plug in, we get like a Ti instead of TO there.
Mhm.
And then we'd get like an Ri instead of IO. So would
Exactly.
those still be kind of the same thing?
Right. Yeah. So if you use the other equation to solve for C2, I think this TO on the right hand side would be Ti. But then also, you know, these I think this guy right here will be Ri right here. Oops. This should not be Ri. This should be R. I think this right here will be Ri. So in the end, they all kind of, you know, it all ends up being kind of the same thing.
Okay.
It might take some algebra to get it, but then you can get the both of them to look basically the same as each other. Yeah. Okay. All right. And so now that we have our temperature distribution, let's plug this into Fourier's law and solve for the heat transfer rate. Okay. And so Fourier's law, remember, is going to be QR is equal to minus K times 2 pi R L dt dr. Okay. And so let's go ahead and plug in dt dr. So if we take the derivative of this with respect to R, what we get is the following. And so we get minus K times 2 pi RL. Okay. And so actually most of these terms go away, right? So if we look back at kind of this form of the equation right here, most of these terms here are constant, right? And so this TO is a constant. And so when we take the derivative of that, it goes away. Everything in this last term right here is also a constant. So all that's also going to go away. And so all we're left with is just the first term. And so that's going to be 1 over R times Ti minus TO divided by ln of Ri divided by Ro. Okay. And then from here, we can see that we have an R in the denominator, and we also have an R in the numerator. Okay. And so we can go ahead and cancel those guys out. Okay. And what we get is QR is equal to, we have, sorry, I lost myself for a second. QR is going to be equal to 2 pi KL times Ti minus TO, all divided by ln of Ro divided by Ri. Okay. And so you notice on the bottom there, I swapped the order of Ri and Ro because there was this negative out in front. Okay. And so I use that negative to basically swap the bottom. Okay? And so the reason for that is that usually RO, since it's the outer radius, that's going to be bigger than RI. And so it's useful to have, you know, the bigger number over the smaller one when you're doing a logarithm. So I just use that negative to flip the order of that. Okay. Any questions on this?
Yeah, can you explain to me how dt over dr in the when solving for q of r became that again?
Sure.
Like why
Yeah,
do
so
we
when we do dt/dr, we're basically taking the r derivative of our temperature, right? And so actually the place that I started with was kind of the long form of the solution, which I have kind of boxed in purple up here. And so what we're going to do is we basically take the derivative of every term with respect to r. And so for the very first term, we have ti minus to over ln of ri over ro. And so all that's a constant. So that's we can kind of ignore that in the derivative. And then we have natural logarithm of r. And so the derivative of natural logarithm is going to be just 1 over r. And so that's how we got this guy right here. And then all the other terms in that expression, the t naught just by itself, and then everything in this last term right here, this ti minus to over ln of ri over ro times ln of ro, all of that is a constant, right? Because ro is just the outer radius. It's not the actual, you know, r function value there. So when we take the derivative of that, that just goes away. And so most of everything goes away except for that first term. And so the derivative of that first term is what I have down here.
Okay, I see. Thank you.
Yep. Okay. All right. And so that's the the expression for the heat transfer rate. Let me rearrange the terms a little bit just to kind of put it in a familiar form that we saw last time. Okay. And so another way to express QR is to kind of group the terms like this. So let's do it like 2 pi k times L all over ln of RO divided by RI. Okay. And this is multiplied by TI minus TO. Okay. And so the reason I did this is to separate, the temperature difference versus kind of everything else. Okay. And just like we did on Monday, if we look at all the terms here, all of these are the physical properties of the cylinder. And so that's significant there because, you know, when we saw this in the planar conduction case, we use this fact to turn it into a resistance. Okay. Okay. And so another way that we can express this is we can say that QR is equal to TI minus TO divided by R cylinder, okay, where R cylinder is equal to the inverse of this guy right here. So this R cylinder is going to be ln of R0 divided by Ri divided by 2 pi k times L. Okay. And so this is an important formula right here, which we're going to use probably on next Monday. This is the thermal resistance of a cylinder. Okay. And so now that's one more thermal resistance formula to add to your repertoire. So far we have, before this, we had 2 thermal resistances. And so we had thermal resistance of a planar chunk, right? And so we also have the thermal resistance for convection. And now we have the thermal resistance for a cylinder, okay? And so what we'll see later on is that, you know, we can do thermal circuit problems with cylinders in exactly the same way. The only thing is we're going to use a different formula for the resistance. Okay. All right, any questions on this before we do another example with the heat equation? Okay. Oh, question?
Yeah, so, or I guess you'll tell us later on in the example, but what type of stuff with this we use the cylinder for?
Oh yeah, yeah. So some applications for cylinders would be like a lot of times you're going to be like say that you're transporting like a large amount of fluid and it's very hot or something, right? So you have kind of hot fluid on the inside and then it's being transported by that cylinder. There's a lot of engineering work that goes in towards insulating that cylinder so that people can touch it and not burn their skin alive,
Okay.
right?
So would like a gas, like the gasoline trucks that you see that deliver the gas for the gas stations be one of them?
Yeah, definitely. Yeah, so that's definitely a system where you would have to control the temperature. So basically, anytime you're transporting anything in a cylinder, a lot of times, you're you want to carefully control the thermal insulation because a lot of times heat loss or heat or heating from the environment is usually something that's not desired in those kind of systems. And so another example that that you can see in your house is in your piping system, actually, right? And so the pipes that deliver, cold water, hot water to your sinks and to your showers, a lot of times you want good insulation there, right? Because for some places, your water heater is usually kind of pretty separate from the rest of your house, or where your bathrooms are and stuff like that. And so if you have hot water that's coming from your water heater up to a shower that might be on the second floor, right? It has to go through a lot of pipes in order to do that. And so what you don't want to happen is, on a cold, winter day, that the water leaves the water heater, but it has to travel through so much piping that it loses all of its heat to the cold weather, right? And so you want to design like thermal insulation for these pipes to make sure that that doesn't happen. So the hot water can kind of reach the second floor, without too much thermal loss. Okay, so let's do another example with the heat equation, but this time let's do a solid cylinder. Okay. Okay. Oh, question in the chat. Using it as asbestos. Okay. And so this time, we're going to do basically the same process we did before, but now our cylinder is solid, so we don't have a hole in the middle. Okay. Okay. And so since we don't have a hole in the middle, we just have an outer radius. Okay. And so we just have an RO. Okay. And then we have an outer temperature T0. Okay. And so just like before, we're going to solve for the temperature distribution inside the cylinder. Okay. All right. And so, we're going to use the heat equation again, but before we actually write that down, let's go ahead and write down our boundary conditions. Okay. And so in this case, we can only see one boundary condition because we just have one radius and one temperature, right? And so the one boundary condition that we have is that T of R naught is equal to T naught. Okay. All right. And for now, let's assume that there's no generation. Okay. And so since this geometry and since we're assuming no generation, it looks very similar to the last one. I'm going to go ahead and start from the general solution. Okay. And so after we perform the integration on the heat equation, remember that we started out with this guy right here. And so we have T of R is equal to C1 ln of R plus C2. Because from the last problem, this is where we started to apply our boundary conditions. Okay. But at this point, we start to see that we have a problem. Okay. Because in the last problem, we were able to solve for both of these constants, both C1 and C2, because we had two boundary conditions, right? Here we only have one boundary condition, right? So we only know the temperature at the outer surface of the cylinder, right? And so in theory, just by, good linear algebra, we know that we'd only be able to solve for one of these, if any, right? And so in order to actually solve this problem, we need to come up with another boundary condition. Okay. But boundary conditions is usually not something that we can just make up out of thin air, right? So we can't just say, oh, I know the temperature, at this other radius, because a lot of times you just can't make that stuff up. Okay. But in this problem, we kind of have to do that, but we're going to do something that's pretty physical. Okay. And so the thing that we're going to do is that since this is a solid cylinder and since we're in 1D, we have to assume that the temperature distribution is symmetric about the center. Okay. Because when you have a system like this where you have radial, we call it radial symmetry, right? Then it kind of makes sense that the middle of the cylinder is either going to be a maximum temperature or it's going to be a minimum temperature. Okay, because if we compare this the temperature, if this is T naught right here, right, on this side, this T naught is being applied to the entire surface of this the entire outer surface of this cylinder, right? So that means it's going to be T naught over here as well. Okay, it's going to be T naught over here and T naught over here. Okay, and so we kind of draw a line that goes from one side of the cylinder to the other one. In order for it to start and end at kind of the same place, we know that it physically it has to kind of have a symmetric profile. So it has to look kind of something like this. Okay? And so let me actually draw that on the next page. Okay? Okay, and so we have a cylinder like this. Okay? And we know that the outer temperature here is T naught, which is going to be the same as the outer temperature here, which is T naught. Okay. In order for basically, if we want to draw how the temperature evolves from one side to the other side, that it has to kind of, maybe look something like this, right? Where the temperature reaches either a local max or a local min in the center of the cylinder. Okay? Okay. And from algebra, from calculus, I guess, we know that whenever we have a maximum or a minimum in a function, we know that the derivative there is going to be 0. Okay. Okay. And so in other words, dt dr at r is equal to 0 has to equal 0 in order for there to be a maximum or a minimum there, right? Or basically, in other words, in order for us to have a symmetric profile. Right? And so let's apply this boundary condition to our general solution. And so we have dt, dr. Okay. And so we're just going to take our general solution here, which is C1 ln of r plus C2, and we're just going to take the derivative of that. Okay. And so when we take the derivative, we get C1 over r. Okay. And then the derivative of C2 just goes away because C2 is just a constant. Okay. And then if we evaluate this at r is equal to 0, okay, what we get is C1 over 0 is equal to 0. Okay. And so what we have right here is something that will break all of mathematics. But in order to kind of rectify this, we say that in order for us to actually have a symmetric temperature distribution, C1 has to be 0. And I know what you're thinking. So if C1 is 0, then we have basically 0 over 0, which is, obviously, breaks math. But, what this basically says is that, whenever we have a solid cylinder, we can't have a term that depends on the natural logarithm. And so, the way that we kind of rectify that is to set C1, which is the coefficient in front of the logarithm term, equal to 0. So I know it is weird, and I know that's not a very satisfying explanation for it. But for cases whenever you have a solid cylinder, any term that's either natural logarithm of r or what we'll see later on with the sphere, which is 1 over r, all of those terms have to be 0 because we can't evaluate the temperature at r is equal to 0 because we're not supposed to get infinity there, right? And if you remember what natural logarithm of 0 is, then that goes down to minus infinity. And so it doesn't make physical sense for us to have, a temperature of minus infinity there. And so whenever we have, a cylinder or a sphere where the center is part of the domain, we just ignore the natural logarithm term. Okay. All right. Any questions on that? Okay. All right. And so now that we've gotten rid of C1, all that we have left is C2. And so we have T of R is equal to C2. Okay. And so let's go ahead and apply our other boundary condition. And so our other boundary condition states that T of R0 has to be T0. Okay. And so, since C2 is the only person left, we say that C2 has to be T naught. Okay. And so T of R, in this case, is just going to be a constant temperature, which is going to be T naught. Okay. All right. And so in this case, when you don't have any thermal generation and you have a solid cylinder, the temperature is going to be basically constant all throughout the cylinder. Okay. And so intuitively, that kind of makes sense because without any thermal generation, there's no way for us to have, for the temperature to kind of go up because it's surrounded by T0 on all sides. And so the only temperature distribution that makes sense is that it's T0 everywhere, right? Because of kind of the radial symmetry that we have here. Okay? Because T naught here, T naught here, T naught, T naught. Okay. Okay. Any final questions on this?
Would that assumption that you made of max or min also apply to that as well, that in the center it would be T naught?
Yeah, because in this case it's all a constant, and so it's when you have everything that's a constant, the maximum is the same as the minimum, which is the same as the constant value. And so if you take the derivative of this function right here, so we take the derivative of just T naught, we end up with 0. And so that also satisfies our condition here. So our middle condition says that that only the derivative of temperature with respect to r has to be 0, and that's satisfied with a constant function like this. Yeah. My cat's not dying. Don't worry. She's just hungry. All right. Any final questions before we sign off for the week?
May I ask a tangent question?
Sure. What's up?
In terms of like having something operate when you, or I guess when you have a machinery operate and you're trying to take away heat from that machinery so it doesn't overheat,
Mhm.
is there a relation between like the operation time versus like how many let's say pipes you have, let's say if you're doing water cool, having pipes, how many pipes you have going through like a reservoir or something like that?
Yeah, so I think
Go
that's probably going to be we're probably going to get into that more once we go into heat exchangers. So heat exchangers is a topic that we're going to go. It's a little bit after convection, so it's it's still a bit of time, but you can make relationships like that. Yeah. Actually next week we'll get into a little bit because we'll be talking about fins, and so fins is not exactly the same thing, but we'll talk about how so fins are basically kind of external structures that you can add to something to help it cool, to basically increase its surface area. And so
Yeah,
we'll be
kinda like-
talking about relationships of like how many fins do you need to add to kind of cool a certain thing. Yeah.
Okay. Yeah, just like how like you like look at computers with how some of them have different heat styles or
Mhm.
heat exchangers.
Yep. Mm-hmm. Yep.
Okay,
Definitely.
thank you.
Yep. Mhm. All right, so that's all we got time for today, and so thank you guys for tuning in as usual. So have a great rest of your day and have a great weekend. Remember the homework's due on Monday, so if you have any questions on that, definitely shoot me an email. But have a great weekend, and I'll see you guys on Monday.
Thanks, guys. Have a good weekend.
Thanks,
Thanks,
you too.
Professor.
Thanks,
Good one.
guys.
Thank you.
Thanks, you guys too.